Hi everyone, have you ever thought about how we designed the perfect box? Engineers do not just guess, they need to be exact to save money and do a good job. Today we will look at topic 6. It is about finding the best value. In math, we use a tool called Differentiation. It helps us find the highest point and the lowest point. Look at the graph. Differentiation helps us find the top of the hole, which is maximum. It also helps us find the bottom of value, which is minimum. Let's look at a real example. Think of a farmer. He has a friend. He wants to make the best garden possible for his plants. We can use math to find the best size for him. Here is another example. Think about the picture. Making boxes. They want to use less paper to save money, but the box must be big enough. We can calculate the lowest cost.
So how do we do this? In this video, I will show you the tips to find these answers. Let's start.
Now, let me show you how we can solve this box optimization problem step by step. Building on the setup, I will now walk you through the mathematical solution to maximize our box volume. So, we understand our goal is to maximize volume. Let's begin solving this problem together. First, let's visualize our box. We are folding up edges from a rectangular metal sheet to create an open top box. The height of our folded edges is x centimeters. The length becomes 12 minus 2x because we fold up x from both ends. The width is 5x meter. We know the original sheet had a perimeter of 100 centimeters. Our task is to find the value of x that gives us the largest possible volume. Now we need to write the volume equation. Volume equals length times width times height. So V equals 12 minus 2x times 5x times x. Let me multiply this out step by step. First, 5x times x gives us 5x squared. Then, we multiply 5x squared by 12 minus 2x. That gives us 60x squared minus 10x cubed. So our complete volume function is V of x equals 60x squared minus 10x cubed. To find the maximum volume, we need to use calculus. We will take the derivative of our volume function. Using the power rule, the derivative of 60x squared is 120x. The derivative of negative 10x cubed is negative 30x squared. So the derivative dv over dx equals 120x minus 30x squared. We set this derivative equal to 0 to find where the volume stops increasing or decreasing. Now we solve 120x minus 30x squared equals 0. I can factor out 30x from both terms. This gives me 30x times 4 minus x equals 0. This equation gives us two possible solutions. First, when 30x equals 0, x equals 0. Second, when 4 minus x equals 0, x equals 4. So we keep x equals 4 as our potential maximum. We should verify this is truly a maximum. Let's use the second derivative test. The second derivative, v double prime, is 120 minus 60x. At x equals 4, v double prime of 4 equals 120 minus 60 times 4, which is negative 120. Since this value is negative, the function is concave down at this point, confirming it's a maximum. Now let's calculate our optimal dimensions. Height equals to 4 centimeters. Length equals 12 minus 2 times 4, which is 4 centimeters. Width equals 5 times 4, which is 20 centimeters. The maximum volume equals 4 times 4 times 20 is 320 cubic centimeters. So by using differentiation, we found the perfect dimensions for our box. I hope that you understand this part. Now pause the video and try to solve this question on your own. After you solve it, you may refer to the workings of this question on the next slide. So this is the solution. In step 1 and step 2, we define the variables and express the height in terms of x using the surface area equation. In step 3 and step 4, we form the volume function and differentiate it to find the critical point. Finally, step 5 and step 6 confirm that the value obtained gives a maximum volume.
Assalamualaikum and a very good morning. My name is Mohamad and Darwisy by Azizan with the method number 309316. I'm going to present a little bit about critical point of function f(x). The derivative basically tells you about the slope of the function at any point. When f(x) equals 0, it tells you exactly the location of the x value on the x-axis, y value of f(x) to see where the y-intercept is. Second derivative is to see whether the slope is negative or positive. Now let's take a look at the question. f(x) equals x squared minus 4x plus 5. Firstly, we use the derivative formula to get the slope, and the answer we get is f(x) equals 2x minus 4. In step 2, substitute 0 to x, which gets us x equal to 2, and then substitute 2 into y, which we get y equals to 1. Use second derivative to check the maximum and minimum point. Since 2 is a positive number, the point is minimum, and the answer is minimum at point 2, 1.
Welcome everyone. Today we are stepping out of the flat world of 2D lines and into the dynamic world of 3D surface. When we work with functions of two variables represented as f(x, y), we are not just looking for a single point on a line anymore. Instead, we are looking for peaks and valleys on a landscape. To find these critical points, we must use a tool called partial differentiation. This allows us to measure how the surface slopes in the x main direction and the y direction independently. Think of it like checking the steepness of a mountain by looking north and then looking east. Let's see how this works with a real example. Here is function to find our critical points. We first need the partial derivative for f(x). We treat y as a constant and differentiate with respect to x, giving us 2y mean 3 mean 2x. We do the same for fy by treating x as a constant, resulting in 2x mean y mean 1 and mean 6y. Now, why do we set to the 0? Well, at the very top of a hill of the bottom of a valley, the ground is perfectly flat for a split second. That means the slope in every direction must be 0. By setting f(x) and fy to 0, we create a system of linear equations. Equation 1 is mean 2x plus 2y, 3. The summary is 3. And equation 2 is 2x mean 6y. Summary is 1. Solving this system will give us the exact x, y coordinates where our surface levels out. This is the most advanced part, so let's go slowly. By adding our two equations, we can eliminate x and solve for y, which give us mean 1. Plugging that back into our original equation shows that x is mean 5, 2. our critical point is located at min 5 to min 1. Is this point applicable by checking our second derivative? We see that both fxx and fyy are less than 0. This means the surface curves downward in both directions, confirming that our is a local maximum. We have successfully mapped these two main variable functions.
Before we end this video, let's do a quick recap of what we have learned about differentiation. You've taken an important step towards strengthening your mathematical skills. Let's quickly recap what you've learned about the application of differentiation. Differentiation is a tool for optimization. It helps find maximum and minimum values of functions in real-life problems, such as volume, area, or cost. Critical points occur where the first derivative equals 0. These points are vital as candidates for maximum or minimum values. Second derivative test identifies maximum or minimum if f(x) less than 0 maximum, if f(x) more than 0 minimum. Method applies to functions of one or two variables. Use partial derivatives and second derivative tests for multivariable functions. Now, it's time to put these lessons into practice. Practice solving differentiation problems on your own using the steps we discussed. Practice is the key to mastering differentiation. So keep up the good work. Before you leave, please take a moment to like and share this video with others who may benefit from understanding differentiation.